Still starting. Yes, finally.
It's very weird. Good morning, everyone. Can you hear me from Zoom? Okay, thanks. Okay, good morning everyone. Sorry for the late start. The room was not open until 5 minutes to 8, so it takes usually 10 minutes to set up the computer and everything. Okay, any questions? You have the tutorial submission and everything. Any questions related to that?
Can we submit multiple times?
Pardon?
Can we submit it multiple times?
Submit it on multiple times? Yeah, I think so. I set it to as I could remember. If not, just let me know. Right? I set it to multiple as I could remember. But if there is any mistake or anything, yeah. So otherwise, yes. But I will mark only the last submission.
Yes.
Okay. So any other questions? No. Good that some of you speak out in Edge discussion forum. That's good to keep it alive, and then so the others know what's going on as well. Okay, what we discussed in the last week was a relay type called IDMT, inverse definite minimum time relays. So the name comes from these characteristics. As you can see here, the relay will, operating time of the relay will reduce with increase in the fault current magnitude. And then how we calculate it, you can look at it in different plots in a different way, but usually it is the fault current divided by some setting called pickup current. Pickup current is the current that you set the relay to start operation, right? Usually the relays, these sort of relays, they won't operate at pickup current, but usually 1.06 or slightly above pickup current, okay? So if you are looking at these characteristics, you can see that it is the relay operating time is inversely proportional to this the time, the magnitude of the fault current, and then after certain level, then the relay time, operating time will not reduce. It's keep it at that constant minimum time interval. Also that we discuss what are the current settings and then what are the time settings of a relay. So depending on, these are sort of definitions. So if you want to set the relay 50% of the rated current of the secondary circuit, then you call it 50%, or sometimes called, let's say if it is 5 amp rated circuit, then we call it 2.5 amp. So you can express these things in different format, okay? And then we discuss about the multiple time settings. So for the same fault current, you will have different operating times, and based on all these explanations, there are operating characteristics defined for these relays. And then this characteristics shown here in the screen is basically coming from one of the standards. So that standards define that when the current multiplier is 4, then when the time setting is half, then the current should be somewhere, the operating time should be somewhere here, right? So using these sort of graphs, one can calculate the operating time. But when it comes to the numerical relays, because mechanical relays, they usually follow these sort of settings, right? It's really hard to come to a certain value in between, right? Because it has sort of fixed or defined characteristics for each levels. But when it comes to a numerical relay, you can define these things using an equation. It's quite easy. Computer knows the parameters, and then they can use those equations to calculate the operating time, like here, right? So you don't have the characteristic curves, but then you have some sort of equations to define the operating time of a relay for a certain time multiplier setting, and then a current setting multiplier or plug setting multiplier. This is again the same 3 curves in IEC standards that you will find these 3 different type of curves. The reason is that their response for a fault is different. Certain curves, if you follow that, the response is fast. Certain curves, it is slow. So as shown here, right? And then if you are looking at coordinating these different type of relays, then you need to look at these characteristics carefully. So that's what we are going to discuss today. And then we did this sort of a small calculation for IDMT relay to find out the operating time for different settings. So when it comes to microprocessor-based relays, as I said, you have this sort of equation, right? It's quite straightforward. A, B parameters are defined for that relay, and TP is the operating time, and then let's say M is the fault current divided by the pickup current, same as plug setting multiplier. Plug setting multiplier is usually used in the old relays where you have that plug, right? But then the terminology they use now is M multiplier, right? M to the power P, P is another constant, and then TDS is again a constant defined to set the time dials, right? So it's the way that the numerical relays are set. So A, B, and P are constant, right? And they are, let's say, if you define that my curve is inverse curve, then you have one setting. Very inverse curve, you have another setting, something like that, right? Those parameters, they are defined in the standards. So as same as the previous explanations, you can see that for different value of M, you can define these curves, right? So in the normal calculations, usually with the numerical relays, you don't have to follow those curves. You can use the equations, right, given to calculate those times. So for example, we will see extreme inverse case where they define the A, B, and P as 28.2, 0.1217, and 2 P equals 2 as respectively those values. So these are the given values for extreme inverse curve. So as I explained, these different curves, they have different time dial adjustments that you need to use for relay code when you are coordinating the relays. I will come to the word coordinating, what is coordinating, in the next part of the lecture. Say, if you are doing a small example calculation here, say if you assume that the fault current is 2 amps, and then if you choose the current time setting, the pickup current as 1 amps, right? This is the pickup current. Therefore, fault current divided by pickup current, which is M, is equal to 2, right? M is always, if you look at it in the explanations or in the given in the previous slide, M is equal to fault current divided by pickup current, right? So if you take that M value, and then if you try to find the operating time, if you select TDS equals 0.5, then operating time will be 5 seconds. And then if you use TDS2, the operating time will be 19 seconds. How do we define which one we have to use? That is the question, right? Which TDS we need to use? That depends on other factors as well as where the relay is located. Like if the relay is initially not coordinating or taking decisions by itself, then sometimes it's good to have the fastest operation, so which is TDS equals 0.5. But we are not sometimes capable of achieving that sort of fast operation when you are doing with relay coordination, because sometimes certain relays have to act faster, and then the other relays usually have to act slower than the fastest relay, which means that you need to take an action based on the operation of the relay in front of you. So in that sort of condition, it will be a different TDS value. We'll look at those things. So only one thing out of this explanation, what you need to understand is that if you want to reduce the operating time, you can increase the value of M by reducing the pickup current. See, you can increase the value of M in two ways. It's not always the fault current magnitude. If you reduce the pickup current, then also M will increase. So which means that your relay is sensitive for smaller fault currents. That is the way that you can increase or reduce the operating time. Not only that, you can reduce the operating time by reducing the TDS. That is also one way of doing it. So you have these multiple options. To control the operating time. So these are the typical relays you will find as digital relays, right? Something similar to this, you will see it during the laboratory test, which is a different brand. These are two different brands, and there are multiple different suppliers, right? And then when you are looking at these relays, they are actually connected to the CT secondary, right? And then the CT secondary should be capable of driving this relay, right? So why I wanted to show that, if you think about this circuit, then I mentioned another parameter in the last Friday's class called burden. What is it? Actually, say if the CT is providing or is the source to run this relay, then CT should be capable of providing certain amount of power, right? Like let's say that power is taken from the main circuit. But then the CT, it's a normal transformer. But what happens is that CTs are designed in a way that your secondary has large number of turns compared to the primary. That's how that you drop the current magnitude. But now the primary side voltage is, there is no voltage transformation. The flux is produced by this current in the primary, right? You can see it, right? Yeah. And then because of the variation of that flux, a small voltage or certain voltage is created across this. Now, because of that voltage, it pushes a certain amount of current going through this. Now, I have a small question here. When you are dealing with CTs, can you keep a current transformer open? The secondary terminals, you keep it open. What happens? Let's say normal transformer that you provide from one terminal, and then the other terminal, if you keep it open, then we call it as open circuit test event, right? You can test it, normal transformer, you supply from one side, other side, you just keep it open. There's no problem with that. Now, with the CT, if you keep the secondary open, what could be the outcome of it? Now think about who produced the flux here. Flux in the core is produced by the primary current. Okay? So the primary current produces certain flux here. Now, what is the principal mechanism of operation of a transformer? If you produce a certain amount of flux, other winding should produce something which opposes the change of that flux, right? Let's say if you apply a voltage, then the other winding will produce a voltage which opposes that change of flux caused by the primary voltage. Now the primary current creates a certain amount of flux, and then it's not a fixed amount of flux, it's changing because you have a 50 hertz current. So that it's a variable. And then in the secondary side, now if you keep it open, what happens now? The winding tries to push a certain amount of current in the secondary because the primary voltage is changing. Therefore, the secondary primary current is changing. Therefore, secondary is trying to create a current in the secondary circuit, okay, tries to create a current in the secondary circuit opposing the change of flux in the primary. Now what happens? If you keep this open, then it can't push that current because it's an open circuit. Now when you can't push the current, then what happens? The system tries to develop the voltage to push the current. Okay, because at the end of the day, it's the d5 by dt. Now the flux changes, it's not opposing, therefore voltage suddenly builds up. So what happens is that if you keep a CT terminals open, then there will be a very large voltage appearing across it. That kills the whole insulation system. Okay, so if you look at it even in the laboratory or field environment, usually you don't never keep the current transformers terminals open. You will see that you can keep them short circuit, no problem at all. You can keep them short circuit, but you can't leave them open, right? So this is, if you look at it in the substations or if you look at it in the laboratory environment, you will see the same. They usually keep with a closed circuit. So that when you are using a CT, usually before connecting this load across it, it should be short circuited. And then once the load is connected, you can take it out because load has a small impedance, right? So if you just take it out, then that could generate a huge voltage, right? So remember that. That's why now when the relay is, say, when the terminals are open, which means that you have a very high impedance across it, right? Very high impedance. Now, if the CT cannot look after that sort of impedance, or CT cannot work with that sort of impedance, then what we do is that we reduce the impedance level. When it is reduced, when it comes to a certain level, then the relay can work without any problem. So that is the maximum impedance that the relay can, the CT can drive, right? So that at that time, CT is not saturated. Saturated means that otherwise the flux goes into a level where that it's not in the linear region. You are working in the non-linear region. Like let's say if this is your typical the variation of the flux. This is the operating region. This is the flux, and this is, let's say, current, primary current, right? And then this is the typical operating region, right? When the flux comes to this level, this is saturated. The flux is saturated. So we don't want the operation of the relay or the CT, in this region. Why? Because then what you measured in the secondary is not proportional to the primary. So what you are measuring in the, let's say, 2 amps, and then you think that the primary has 100 amps, but actually primary has 200 amps. So then your all measurements are wrong. Therefore, always we need to operate in this linear region, not in the saturated. Okay, so for that, as I said, these relays should be low impedance. If it is high impedance, then the CT will go into this saturated level. So what happens is that if the relay impedance is large, then the operating characteristics goes to the saturation region, because the relay can't push that much of current through that sort of impedance, right? So to avoid that, you need to go with a lower impedance relays. And then that is what we call as burden. Burden is the impedance of the relay. Usually when you are doing the calculation, sometimes you need to even consider the resistance of the wire, because that is also resistance, right? And then probably sometimes that you have a fuse in the circuit. So you need to consider the resistance of that fuse, right? Addition of all those things will give you what is the total burden across that CT. Even the CT winding has some resistance. That is also a burden, right? So all the resistive components in the secondary circuit can be called as burdens. Okay, and usually you can see that these are the second bullet point shows the typical power ratings of CT. They are very, very low rated. They are not very high, right? With that low rated, then you can't connect very large impedances across them. So that typically, as stated here, the mechanical relays is around 3 VA, which you can't use with 1.5 VA. Then with the 1.5 VA CT, you may need to go with a electronic or numerical relays, right? Pardon?
Why does 60 volt and ones exist in your typical 3? Like, is that just all the design cheap ones, or are they?
No. See, that depends. That depends on the system requirements.
Yeah.
Let's say, and also the cost. Right? When you go with the higher VA, they're expensive. So then, as I think the first or second lecture that I mentioned, that the cost is one of the driving factors. So when you're dealing with these sort of like, let's say, you need to look at how many customers you are going to protect, right? What is the cost of total protection scheme, which should be at the end of the day, the cost of that protection goes to the, like, let's say, number of customers, right? So then sometimes that you don't need to go with very high rated ones, especially when the primary current circuit is let's say low, then you can have lower rating there for the CT as well. So it's different factors, right? Mainly I would say that economical factors and one of the driving things there. Okay. Now, what is this? It's fine. I think it's some sort of a, this is, yeah, good. Okay. Now what we are going to look at, how are we going to use these sort of relays with these given relay characteristics, IDMTs, a radial feeder. When you're looking at this sort of feeder, say I have a relay here or circuit breaker 1, and the relay 1 is driving that circuit breaker. Okay, so if you put a 1 at that point, then of course whole feeder is protected now, right? Let's say if there is a fault here, or if there is a fault here, or if there is a fault here, you can see that the circuit breaker can measure it, right? Circuit breaker can disconnect that line. What are the advantages and disadvantages of that sort of protection scheme? Say that circuit breaker, you can say that, okay, I can set a fixed time, right? I don't have to even go for IDMT. I will say that instantaneous relay, right? I will put an instantaneous relay at circuit breaker R1 as R1, so that for any fault, my feeder will be disconnected. Great, right? Very fast operation. Now, what are the problems associated with that? What are the challenges there then? What do you think?
And takes out the entire network.
Yes. The major issue associated with this is that for any fault, now the whole feeder will be disconnected. But then, let's say, if there is a fault at IF1, right, only the wind farm and that domestic connection should be disconnected, but not the other guys. So what happens is that when these regulatory commissions came up, they are looking at the performance of the utilities. How do they look at it? they have different parameters, measurable parameters, saying that how many customers lose the power per minute, per year, something like that. There are many different, if you look at the power system by the market scores, right? So then there are ways that you can look at the performance, right, of a utility. So now look at here. So if I'm an engineer into one of these utilities, and then I'm thinking, okay, if they are looking at these numbers, right, one way is that I can improve the feeder, right? I will improve the feeder means that I will avoid the possibilities to disconnect it due to loads. That's one way. But then you will find that, okay, can I avoid, touching a tree branch, right? I can have some sort of clearance, but then the amount of money that I have to spend every week, probably I have to send someone. Can I avoid thunderstorms? No, no way. Can I avoid, let's say, if somebody is doing some, like let's say wrongdoing things, someone put something on the line and then it's disconnected, right? So that could, you don't have any control over those sort of things. But then ultimately, as the service provider, you are losing money because you have to pay compensation and a lot of things, and then you can't strict into the regulation limits. So then what they come up with? Okay, then instead of one breaker, what happens if I put couple of breakers like this? Right? So I'm putting circuit breaker 2, circuit breaker 3. I'm putting 3 circuit breakers now. So the purpose of putting these breakers is, now if there is a fault in this section, then this circuit breaker will disconnect the line, but still the other people in this, or other customers in this feeder is supplied. So that the number of customers that you lose is smaller. This is the point where that, these Noja Power and all these guys came into the market in probably 2000s. The reason is that they came up with a design, like earlier circuit breakers are bulky and you just installed it in the substation, right? But they came up with a solution saying that, okay, I can put one on the poles and then in intermediate sections, right? So probably not only them, probably there are Siemens, ABB, probably everyone has something, right? So, but then came up with this sort of design where that you can put that sort of small breakers in these locations. Then they came up with the name auto reclosures, right? So why it is rather than a breaker is a bit bulky, huge, and then you can break huge amount of current, right? Auto reclosures, what they do, they detect these faults and then open, and then again they will close it. Open and then close it. Why? Because then if it was a sudden incident that you don't have to have the complete disconnection, then there is no problem in the system, permanent problem. So that they close it. See, if the system is running well, keep it there. If not, open again, right? And then close again. Probably they will do, I think, 2 to 3 times, and then keep it open if there's a problem, right? So that reduces, you don't have to send crews, number one, because now the system is running, right? For a small, some sort of an issue, a tree branch, suddenly touched, or wind, because of wind something happened, or animal went through on or snake short circuited the 2 lines, these sort of things, you don't have to go back and then fix it, right? Those things sort of self-healing things. So that was one of the advantages. And the other advantage is that, as I said, the number of customers who lose the power is very minimal. Now, but once you introduce these sort of things, now another important question comes. What happens? How do I control, like let's say, earlier I control this circuit breaker 1, disconnected the whole system. Now, when this fault IF1 occurs here, I have to stop the operation of CB1. Before CB1, I have to operate CB3, right? So how are we going to do that? That is the question. Because now if the circuit breaker 3 operates, that's fine. But for this fault, still circuit breaker 1 operates, then there is no point of putting circuit breaker 3 there. Right? So what we want to do, we want to operate or we want to coordinate these circuit breakers in such a way that the circuit breaker 3 will look after these IF1, but if it cannot look after that, then the circuit breaker 2 will operate. If both of them cannot look after this IF1 fault, then circuit breaker 1 will operate. So you have to have some sort of a communication between the relays. Nowadays, probably you are in a sort of communication very advanced era. So probably someone could suggest that, okay, you put a communication link between them and then this guy is doing something and then send the message, right? You can do it in that way. Yes. But in, let's say 20 years back or 30 years back, right? The communication was not the best for using, to use with this sort of things, because one is it is expensive, because you may have to put a separate let's say link, could be microwave link or optical fiber link, right? Not cheap as now. And the other thing is that the reliability of those. You need to have some sort of a reliable way to have that communication. Because if it is not reliable communication, then always circuit breaker 1 could operate, or circuit breaker 1 will never operate, right? So therefore, that the settings or for these relays, you can, the cheap and more reliable way of doing it is that use relay characteristics, right? Use the relay characteristics and then you define the operating times and everything for these relays, so that they will work in such a way that for a fault after CB3 will definitely look after that. If that relay fails for some instance, then the CB2 will look after it. So you can set the relay characteristics in such a way that there will be a good coordination between these relays. So that is what we are going to learn now. Okay? So when you are looking at that sort of coordination, one way is that how do you discriminate the faults? Like as an example, how do you discriminate the fault 1 from fault 2, like based on the location, right? How do you do that? So in one way is that, before going to that, there are two types of discriminations that what we are going to look at. But what is discrimination is that relay at B, right, at the bus bar B, must operate for a fault between B and C. Between B and C, relay B must operate. Relay A must operate for faults between A and B, not B and C, right? So how do we discriminate those conditions? Like how the relay A is identifying whether the fault is in front of B or before that, right? So that is sort of called discrimination. Then we are going to look at that how we set that discrimination by setting different times for relays. And also that we are going to look at how the discrimination can be set by the current, like magnitude of the fault currents. So the relay can operate in different times, so that you call discrimination by time, or relays are operating based on the current magnitudes. Then we call it as discrimination by current. So discrimination by time means that you add a time delay between the relays. like as an example, it's quite easy. You set the operating time of the relay B to 1 second, and then operating time of relay A to higher or speed or lower. Let's say the operating time should be higher or lower for the R1 compared to R2. Like let's say R2 operating time is 1 second. What should be then R1? Is it 1.05 or 0.9? Yeah, 1.05. Yeah?
Well, you're going higher than that.
Yeah, you have to go higher, right?
You should go higher.
Yeah, because the problem is that then for a fault here, when this guy is operating, this guy is still waiting. And then if this guy cannot identify, B cannot identify it, then yes, A will operate after 1 second, right? So that discrimination by time is basically works by adding time delay between the operations. So it is very simple. So the usual practice is that when you go towards the generator, the operating time of the relay will increase. When you are going towards the generator, operating time will increase. So that is how you set the relays. So if you do that, if you are having the highest operating time closer to the generator, which means that opposite of it is the fastest operating time or minimum time to operate is set to the relay furthest away from the source. So the last one will operate faster, so that the first ones will not operate. So that is the way that you do it. Yeah, this is the maximum time is closer to the source. So the time delay that you set between the operation of these two relays is called as grading margin. So when you are looking at the grading margins, I will come to that point in a later slide as well. There are certain factors which defines the grading margin for relays, right? It's not only just arbitrary number, because relays have their own errors, circuit breakers operating time, and then probably communication channel time, and all those things adding up together, right? So we will come to the grading margin thing in the next slides as well. So remember that it is the time delay between the two different or two consecutive relays. It's just adjacent ones, right? The operating time delay between them. So in this, if you are looking at in this figure, operating time at relay 1 is the slowest, TOP3 is the fastest. And then you can see that if you want to find the operating time of relay 2, that is basically the operating time that you set for relay 3 plus grading margin. So if you have that grading margin, if you know that grading margin, then always TOP2 should be a value okay, if you have certain number of, let's say there are limitations, right? If you can't select whatever the time that you want, but if the relay manufacturer provides you these are the times that you can use, then if this is the condition that you need to satisfy, say TOP1 is equal to, let's say, 0.5 seconds, and then my grading margin is, let's say, 0.25 seconds, right? And then the given times for these relays, given operating times, say 0.5 1, 1.5, 2. Right? Now what should be the operating time of TOP2? Say, you know TOP2 is TOP3, oh sorry, this one is TOP1, 3, sorry, not 1. That is the furthest away one, right? So the relay 3 is 0.5 seconds. Grading margin is 0.25 seconds. What is the operating time of TOP2 now? What is the one that you want to set? 1. Why shouldn't I go for 0.5? Because, okay, if you have, let's say, to make it clear, I will change this like this, okay? These are the operating times. Which one do you select? These are the operating times of given operating times for relay 2. Which time would you select? 0.8, correct. Why is that? Why you don't go for 0.7?
That is smaller than 0.75.
Yes. So why we don't want to go below that? Because we are not sure. We need at least 0.75 because grading margin gives you the minimum difference that is required, right? So if you are going above that, that is fine because then that can keep that, coordination properly. But then if it is less than 0.75, it could, it may not, we don't know, right? So, but one of the main things with designing the protection systems is that you need to have that security and then reliability. So that's why that you go for that. Okay. So as I said, the grading margin, what factors that influence? See, the circuit breaker will have some operating time. So definitely that needs to be considered because circuit breaker at 3 will operate. Let's say it takes 100 milliseconds. Then you need to consider that time when you are calculating the operating time for the circuit, the relay at 0.2. The typically 150 milliseconds for old oil circuit breakers, but maximum 50 milliseconds for latest SF6 or vacuum ones. So what happens is with the technology, the relay operating time became faster and faster, right? And then that is the max, even 50 milliseconds is the max. It depends on the arc interruption process. And then relay overshoot. So typically only, this is for mechanical relays, right? Overshoot means that, can you remember that the disk, it can go further a little bit of, more than what is required, right? So those are the overshooting of those relays. That's in a control system probably if you learned that overshoot and undershoot, things like that. So it is coming from those control mechanisms. So you need to allow those overshoot times. And then basically that is caused by the kinetic energy and in the disk when it is rotating, and then it could go beyond what is required. And then errors and safety margins. This is basically, errors are even applicable for numerical relays. You can have errors there, right? And of course, you need to keep some sort of a safety margin because which are encountered for unforeseen errors, right? There are errors that we never think about. So that you need to keep a small safe margin for that as well. And sometimes there are CT errors, right? And then sometimes there are the errors in the sensors, right? A lot of type of errors, right? So that you need to think about all those things. And usually grading interval of 0.5 to 4 to 0.5 seconds are used for electromagnetic relays with oil circuit breakers. If you have oil circuit breakers, you need to put a large gap or time gap between those two relays. But if you go with the numerical relays, you can see this 0.25, 250 milliseconds is enough, right? Half of the mechanical relays, right? So that those are the big advantages of these numerical relays. It's not just the they are cool, right? But then you have a lot of other advantages. Like this is one of them. Operation is so fast, and then you don't need to keep huge Grady margins. Okay. So then, why we don't want to keep large grading margins? Why we don't want to keep large? So this is an advantage. Then why we don't want to keep it? Anyone from Zoom? Why do we want to? Why we don't want to have large grading margins or grading intervals?
Because they're too large once
Yeah.
you
Yeah, so then, which means that you have to design your circuit in a way that it can bear that of, fault current for that longer time period, right? Because you are reducing the time, and which means that, let's say, like in your, when you design the circuit breakers, towers and everything, then you need to think about, okay, this has to sustain the fault for that long period, right? So that introduces extra cost, right? And also the customers might feel it or things like that. Anyway, okay. So now the issue with the discrimination by time, that's what we are going to look at it here. Say if you have the discrimination by time, we know that operating time of relay R1 is the slowest, but you can see that by looking at this diagram, the fault current is larger when you are closer to the source. But then which means that when you are away from the source, IF3 is small, but this relay is operating so fast. So when the fault current is smaller, you are operating faster. When the relay current is large, when the fault current is large, you are operating slower. Would that be good? No. So that is the problem, one of the major problems. You can't just say that small operating time is good, because the fault current needs to be considered. So this is an example here. Now, that is the main disadvantage of this method, that the longest fault clearance time for the fault closer to the source, right? Which is not good. And then, because the severity of the fault is high when the fault magnitude, current magnitude is high. Got it? So now, therefore, we are looking at another way to discriminate, which is called discriminate by current. How does relay operation can be discriminated or coordinated? By current. So, idea behind this method is that the fault current will reduce when you are going away from the source. So that you can consider that factor when designing the relay coordination, right? Why the fault current becomes smaller and smaller when you are going away from the source? Why the fault current? I said that the fault current is lowest further away from the source. What is the reason? Simple reason. Yeah, impedance of the line. So impedance of the line increases when you are going further away from the source. So that is the only reason, right? So that's what we are going to consider. Even this impedance will be considered in some other protection schemes. We will discuss that. So this is one way of looking at it. You have three different faults here. Let's say the three different fault magnitudes are 13, 8.77 and 8.2, right? These fault magnitudes. So what we do, now we are going to, instead of looking at the operating time, what we are looking at is the pickup current now, because that is also a parameter you can change. So what we do, we set the relay at A, right? Its operating current is about 8.2 kiloamps, sorry, the 8.7 kiloamps, right? Relay at B, the operating current is 8.2 kiloamps. Why I set it like that? Say this relay at this point should look after any fault from A to B. So if there is a fault closer to the B, then what is the fault current? That is 8.77. So if I want to set this relay to look after that, then the operating current here should be 8.77. Understood? Because if it is 8.77, right? So if this is 8.77 kiloampere, I pick up. This is I pick up is equal to 8.2 kiloamps. Okay. So we didn't consider IC because IC there could be some other fault current here, right? I didn't put it here, right? So that's the pickup current of these two relays. Now you can see that if there is a fault somewhere here, relay A will not operate for that. Why? The pickup current is not sufficient if the fault is somewhere here. But if the fault is somewhere here, then this guy will operate, right? And then the B, if the fault is beyond C, it won't operate. It will only operate if the fault is between B and C. It's very simple mechanism, right? Now, so the relay B, that will protect the line BC, and then relay A, that will protect line AB, because that's how we set it, right? Now let's look at what issues associated with this sort of scheme. Before that, I'm happy to give you 5 minutes break. And it seems that my Friday lecture is not recorded for some reason, because it's recording only through Zoom, not through the system. So if I can't find it, then just let me know. I can explain things, we have done it in that class. Guys on Zoom, do you have any questions? least couple of weekends we had without any rain, right? You are doing masters, or you are doing master, right? You are too, right? You are master or no? Pardon?
This one.
Or this year?
Yeah.
Is this the last semester?
No, I have one more to go.
Oh, one more to go.
Next time we are facing semester.
So you are doing that industry placement thing, or
Yeah.
which master program you are doing?
Oh no, I'm doing bachelor and master.
Ah, bachelor in one.
Integrated.
Ah, okay.
Integrated.
Integrated one. Okay. So the next you will have that long.
Yeah. I'll have
Have you
that.
already found a place?
No, we haven't found. We haven't found it. The process just kind of started, and we just met
Yeah. Are they going to find it for you, or?
we can choose to either self-source or for company source.
Mm.
I haven't decided yet, but they say if you don't have the connection outside, then
Yeah.
they have a list projects
Okay.
available.
What is your interest?
Mine is power system. Because I don't. It's not me. Because I took the renewable
Yeah.
last semester.
Mm-hmm. Did you find a place, or thinking of, like you are thinking of a specific place, or?
More like a specific industry. The company is, I don't exactly know like a few, I mean I know a few big ones, but
Yeah.
it's not really my focus.
Mm.
I'm mainly interested in just the renewable side of power system.
Mm. So you're looking for a consultancy firm, or a?
Research is fine too. Yeah. I want to go into like research role, so I can relate to integration and stuff.
Okay. Okay, I'll start again after a short break. So in the discrimination by current, the first figure shows the calculations that we have done so far. Now, usually these sort of overcurrent protection schemes for radial feeders are common in distribution systems. They are not for transmission systems. One of the issues associated with the distribution systems is that the sort of short circuit capability of the system can change very quickly, because it depends on number of sources connected to the system and number of lines connected to that, and a lot of things. So what happens, let's say when you set your parameters of the relay based on this, and then suddenly the short circuit level of the system changes for some reason, like number of transmission lines connected to this substation has dropped, right? But still it's capable of supplying power, but their short circuit level dropped. Now if you have the short circuit level changed, then what happens is that will affect the short circuit current or fault currents in different locations. For this 11 kV with 250 MVA, fault current at this location is 13.12. But now when this is dropped to 130, the fault current dropped to 6.8 kiloamps. Similarly, the fault current magnitudes in these locations will drop as well. The line impedance will be the same, right? Supply voltage is same, but there is some impedance associated with this guy, short circuit impedance. That impedance has been now increased. That's what has happened. When the short circuit impedance increased, then the fault current drops. Now, if you use the same settings as what we set here, right? We said that the relay A will operate only when the magnitude of the current is 8.77 kiloamps, right? So if you look at the fault current IF2 now, that current is reduced or less than now below 8.77. The current is here less than 8.77, right? You can calculate it the same way as I put it there. If this is dropped from 13.12 to 6.08, then 8.7, it will be lower than 8.77. So it will be lower than 8.77 means, now where should be 8.77 thing on this line? There should be a location, right? Because this one is 6.8, and then which means that can there be 8.77 somewhere here? No, because this value is less here, right? So then what happens is that relay A cannot fully protect the line AB, right? Because of the short circuit level change. So that's the problem with discrimination by current. If you only look at it, under one condition you set the relay parameters, and then because I set it based on the largest fault currents, it won't work then. Then what is the other option then? You will consider not the largest. What happens if you set the smallest fault currents? Then it should, then it should work for the largest, right? If you set the smaller values, then it should work for the largest fault current without a problem. We'll look at it. Okay, now what happens? If you set the smaller fault currents here, yes, it will work, but when the system is running with this, the first case where the short circuit impedance, the power is high, then where is, let's say if you set it to a certain value, then that smaller fault current will appear somewhere here, which means that this relay will operate for faults beyond point P. So that is another problem, because if you set it to a lower fault current, when the relays are operating under full short circuit power, then the relay might, the relay A might trip for faults between B and C, right? There's a possibility that relay A might operate for faults between B and C. So that is an issue with this sort of system. Then that's why we have introduced, or we are introducing something called discrimination by both time and current. So that is the best coordination between the relays. How are we going to do, or what is the purpose of doing this? So what we are looking at is, say we are using these characteristics, relay characteristics, to coordinate or prepare a coordination between these relays. That is called both time and current discrimination. Definitely that can be done only with IDMT relays. Remember that. Not with fixed time relays, not with instantaneous relays. You will only do it with IDMT relays, right? The coordination, discrimination by both time and current can be done only using IDMT relays. So what we do is, let's say if there is any, let's say between B and C, the faults are looked after by the relay B. Okay, so if you are going along one of these curves, because let's say for a relay at B, you can fix its pickup current because it's a physical setting. You can fix the time dial setting. Once you fix those two, then you can say that you fix the operating curve. If you fix the time dial setting, right, and then if you fix the, let's say, if you know what is your pickup current, right, then you are working along one of these curves because your time dial setting is fixed now. Let's say you are working on this one, this curve, right? So you set the time dial setting of the relay at B for one of these characteristics. You say that, okay, my time dial setting is 0.5. So this is the operating curve for that. Now, I have a certain pickup current for this relay, right? I set that pickup current based on the lowest fault current in this line, which is the fault current somewhere here, right? The lowest value. And then my operation looks like this. Say when you are moving from C to B, the operating time decreases along this curve down to here. Now what I do, when I come here, now relay A should look after me. Relay A should look after me, not B, right? So what I do, I add a grading margin. So if I add that time grading margin means that let's say for the same fault, relay A will have an operation time of, if I add some number. So that, let's say in this particular case, I added 1.5. So if you add 1.5 to 0.5, now the operating curve at relay A is this curve, the green one, right? Now I can set the pickup for this relay as well. That relay, you can see that multiplier pickup plug setting multiplier is fixed because I am operating at this point, right? And then if I set that plug setting multiplier for a certain current, that current is actually here. That is the corresponding current. You will understand this when I am doing another example, right? So in the next, I think, couple of pages before, after this. But what you need to understand here is that you are jumping from one curve to another curve. And then now I fix the operation of that relay on this curve. So when I am moving from B to A, again operating time is reducing. So it's like first initially it started somewhere here, operating time came here, suddenly jumped because of the grading margin, and then again it is reducing now. It's good because when you are going towards the source, still the operating time is reducing. See? So that is the advantage. If you have another relay there, you jump from here to the other curve, and then going along that curve towards the source. So it's like you are changing the operating characteristics of the relay when you are going from one relay to the other one. So these are the steps. There is a very easy way of doing this with a table, which I will explain it to you. So in these sort of scenarios, usually the problem is that where should I start on these curves, right? Which curve should be the first curve that I need to consider? Typically, the one which is, let's say, furthest away from the source will use the lowest curve, and then you start from there, and then it goes up like that. So it's, if you go further up, again one level up, and then reduce, again another level up, right? So it's always you need to look at the most remote relay from if you are looking at from the generator location, the furthest away relay will select the lowest TMS, and then other TMSs are selected based on the grading margin, which we will discuss. this example, I will talk about this one first. Two examples here. Since I talked about the discrimination there, I would start to talk about this one. Right? So when you are dealing with this sort of examples, say, now what we are going to do here is we are going to calculate the coordination of these relays, right? What are the settings for these relays to, let's say, to protect these feeders. Settings that you are going to set on these relays to protect these feeders, right? So some example conditions, like some conditions are given, always those settings depends on the given conditions. So the number one is that relay should not operate for 25% of overload. What does that mean? Yeah, so the pickup current should be more than 25% of the load. Like, which means that the relay will allow 125% loading. Because sometimes, during the summer conditions, we know that sometimes our transformers are loading, basically overloading, right? Overloading for a short time duration, sometimes they allow it, because otherwise you may have to change your whole network upgrade, which is expensive. So sometimes they allow, okay, we will allow it for 2 hours, 125%. Now if the relay operates within that region, then you will be in trouble, right? The relay will disconnect the line because you are operating over certain limits. So to avoid that, sometimes you set, okay, the relay should not operate for 25. That's the one condition here. Second one is 25% margin was used to avoid unnecessary tripping. So that is the same. The relay should not operate for 25% overload means that 25% margin was used to avoid unnecessary tripping. Use the maximum fault current to determine the relay settings and check whether the operation is satisfactory for minimum fault current. That is what we are going to do, right? Maximum fault current to determine the relay settings. Remember, relay settings are always set based on the maximum fault currents, right? So that we will discuss. And then clearly say that TMS is always in the multiplies of 0.05. So you can't select any TMS. It's 0.05, 0.1, 0.15, 0.2 like that, okay? And then the grading margin has to be assumed at 0.4 seconds, right? So that is also given. Now we will go back to the question. These are the conditions that we need to satisfy. Okay. The step one is we need to look at what are the load currents associated with these relays, right? Or what is the load current going through these lines, right? Assume that the power factors, if the power factors are not given, you can assume that they are unity power factor loads, right? So in this particular case now, the power going through line BC is 80 amps. So that is the full load current. Got it? That is the full load current. And then between A and B, what is the full load current? 240, because it's the load at B plus 80. Another part we need to calculate usually, but it is given here. What is that? Fault currents, right? So see, usually it can be 3-phase or line, this can be line to line, right? And then mostly this can be 3-phase, right? So then, but I have given it to you. I'm not going to calculate it. It's like in the real scenarios, you need to calculate the fault current at C, maximum, minimum. Fault current at B, maximum, minimum. They are the same here as well, right? Because it's the same location. and then fault current at the beginning 3000 and 2500. So those are given. Now what are the overload current conditions? Because we need to consider those as well. You need to multiply this by 1.25, which is 100, 240 multiplied by 1.25, which is 300. Okay. Then we need to select a suitable CT, that is the current transformer, right? Current transformer secondaries can be 5 amp or 1 amp, depending on the standards people use, right? So if you are using a whole lot of numerical relays, 1 amp is enough. But if you are using the numerical, the mechanical relays, usually it is 5 amp, right? So, but in this case, assume that we are using 1 amp. Okay. So if you are using 1 amp, and then what is the maximum load current that the CT that measures at this point? Here, what is the maximum load current this CT will measure? The CT at this point, what is the maximum load current this CT can measure? Or is measuring 100 amps, right? Because this 100 amp is going through this CT. This is not going through that CT, right? Because it is in front of that feeder. Okay, so that is, therefore I can say that okay, roughly 100 to 1 is a good selection, but depending on sometimes that someone could say that 100 is, you know, it's the boundary now, right? Probably you can go one step ahead, 150 to 1, right? So let's put 100 just to make it easier for the calculations, right? And then the next one, the relay at this location. This 200 amp is not going through that CT. Therefore, you can select that CT as 300 to 1, right? And then in the question it says that current setting, use it in such a way that 25% margin was used to avoid unnecessary tripping, right? Which means that when the 125% load is going, still you are not sure whether it is going to, because if you just set it to that, relay might have some errors. Therefore, our current setting is 125%, right? If this is 100 amps is the more low overloading condition, then the current setting is 125 amps, right? Current setting means that you can consider it as pickup, right? They are the same thing. What is the pickup or current setting for other relay? The relay at A, it should be 240, 300 multiplied by 1.25, which is 375 amps, right? So those are the settings, not in the relay side. Still our calculations, we did it in which side? Primary circuit side. Okay, so you have to look at the corresponding parameters in the other side by dividing it by 100, and then the other one is dividing by 300, right? So that is the primary side, secondary side. This is 3.75 divided by 300. How much is it? 1 point. 1.25, right? This is 1.25, and then this one again 1.25. Got it? So both relays you can set the same current settings. Why I divided by 300? Why did I divide it by 300 in this one and then the other one divided by 100? Yeah, that is the turns ratio of the current transformer, right? Because 375 and 125 are the currents in the primary circuit, and then you need to divide it by corresponding turns ratio to bring it to the secondary side. Now, the other question is that what are the maximum fault currents in the relay side? Maximum fault currents in the relay side. How do we do that? You divide the maximum fault currents by the corresponding CT ratios, right? So then here maximum fault current is easy, 15. This is 20, right? Here, is it 20 or something different? Yeah, so 20 divided by 3, which is 6.66, right? And then this one is again 10, right? So that's related to the same relay current or the corresponding relay current for those faults. Now we need to find the multiplier, M. This is also M. You found it for numerical relays, or current setting multiplier, which is basically the fault current divided by the pickup current, or setting, right? Plug setting or current setting, right? So now in this case, the current setting is 1.25. That is 15 divided by 1.25, which is, how much is it? 3? Sorry, 12. Is that correct? Divided by 1.25, 12, right? And then 20 divided by 1.25, which is 16. This one becomes 4.1, because it is again still the 1.25, and this one is 3.3. Doesn't want to. It should be 3.
Shouldn't be 8.
Pardon?
Shouldn't be 8. 10 to
Oh, sorry. Yeah. It's T.
And the elements.
This is 5.3,
Yes.
right? Sorry. This is 8.
Yeah,
And that's why it doesn't allow me to write wrong.
it's really funny.
I don't know why.
Yeah, it's in that weird sleep thing.
I'll write here. Oh yeah.
Right, 8 is the word, one word.
Nah, it's
Yeah.
right. So now we know the multipliers, right? And then we know what are the no, first we know the maximum fault currents. Based on that, we know the current multipliers and in different locations. And then everything is for maximum fault currents. So now the first thing is that we need to select one of the relays, their characteristics, time characteristics. So what we do, we will say that we will look at the time multiplier, right? We will look at the time multiplier as 0.1, right? So because it's given somewhere, where is that? Time multiplier settings. If you go into the characteristics, that is in the next slide, that's why. Yeah, here. Can you see the characteristics given here? Which one is this, let's say, lowest TDS? It is 0.1. Lowest TDS is given as 0.1. Right? So, if the lowest is given this one, then we need to select that 0.1 for the furthest away relay, because that is given. That is the given smallest TDS setting. Now I have selected that. If you select that, then since we know the multiplier values, m equals 12, then if I go back to this characteristics, this is 10, and then if you have somewhere here, the 12 should be somewhere here. Right? Okay, so then you can roughly estimate, right? In this particular case, the curves are not very accurately given for you, but then in the, say, real calculations, it can be the relay characteristics using those equations. Then it's easy, because it's, you just have to substitute the values, right? But here, if you assume that now roughly, right, let's say, hold on, yeah, this is roughly somewhere here, close to 0.3, right? So when the operating time, when we consider the operating time, it's better to consider the higher side of it, because then when we design something, we design it for 0.3, not to 0.29, right? So that which means that if it is 0.29, then still the system can survive those faults, right? Because you are designing it for 0.3. So in this particular case, I will say that this is around, say, 0.29 or 0.3, right? Based on the values, see? Based on the values, it is 0.29, 0.3. But if you design, when you design it, it's good to go with the 0.3 in reality, right? 0.29 if you are not sure, right? So it's the good approach of it. Now, if you look at the other one, 16. So in the same curve, 16 is somewhere here. Right? 16 is somewhere there. Because we are in the same curve, because we are using the same relay. Now, if you go back, look at here, that initially I calculate the operating time at point C. Now I am going to calculate the operating time of the relay at B. So if you look at that, it's roughly 0.26, right? That's coming from other value, but if you look at it here, it's roughly below 0.25, right? I have just taken this graph for the explanation, right? Don't look at those values exactly, okay? So if you go with the real values, then we can use the equation, right? So, but with the equation, it's a bit hard to explain these things. So that's why that I'm using the curve. Now, once you find that, then we know the operating time of the relay at B for this fault here is 0.26 seconds. Now, relay A will also operate for a similar type of fault at this point. To avoid the operation of relay A for that fault, we need to increase the operating time of relay A by 0.4 compared to the operating time of this relay. See, the relay here operates at 0.26, but relay A should operate for the same fault at 0.66 with 0.66 seconds time. Why? If you go back and then look at the notes, it's clearly say that grading margin was assumed as 0.4 seconds. So that the operating time of that relay should be 0.4 seconds more. Okay, so that is 0.4 seconds. That's why it has become 0.66 seconds. Now, if it is 0.66, now we need to go back to this graph again, right? What is its corresponding setting, plug setting? The current, the setting which is current setting multiplier, which is 5.3, right? That setting is 5.3. For 5.3, the operating time should be 0.66 seconds. Now you go back to this figure, right? Unfortunately, I can't enlarge it here. So, now if you are looking at somewhere here, 5.3, right? And I need minimum operating time of did I say write the correct values there? Yeah. Yeah, 0.29, 0.26, 0.66. That's correct. So we need to look at 0.66 operating time, where 0.6 is somewhere here. Do you agree that 0.6 is somewhere here? Okay, along that line. Operating time should be below that or above that. Operating time of relay A should be below this or above that. Should be above. Because it should be, if it is below, which means that the relay will operate faster than we think. It can be slower, because then it can, there is no miss operation of relay 1 or relay A. So anything above that. Now, what is the corresponding PSM? That was or plug setting multiplier or current setting multiplier, which is 5.3. So somewhere here. Now you go along this one, you hit this curve here, right? So you can see that curve, the point where that the operating time for 5.3 is above 0.67. Can you see that? This point is above this line, right? So you can consider that this can be a good candidate for your operation. That is a good candidate. Now let's say somehow if your answer in the previous answer required operating time was somewhere here, then this is not a good candidate. Then you need to go further up. Got it? Because this point is a fixed point. We fixed it before. We mentioned that our plug setting multiplier or current setting multiplier is 5.3. That is always fixed. So operating time for that fixed time should be above the required operating time. Required operating time is, in this case, 0.66 seconds. But if it is more than that, then you have to draw that line and then find which curve is going beyond that. Okay, now, so that we define, okay, this is the, and since this point is a good point, this is for characteristics for relay A, right? So now I define it as point, the relay. Based on that, we use the characteristics are given as TDS. Use TDS equals 0.2. Right? So that's what we used. TDS 0.2, we used it here, second curve. Now, once you have the TDS, the second curve, then we need to go back and then look at what is the actual operating time, because it is not 0.66 anymore, because we moved the point a little bit upwards into this curve. Therefore, my actual operating time is somewhere here. So that's you calculated as 0.85. So that is the actual operating time based on the selection of TDS of 0.2. We know that current multiplier or the plug setting multiplier is 5.3, and then we have selected the curve TDS 0.2, and therefore based on that you can find the corresponding actual operating time. And once you know that, then you can go and then look at, okay, so that is for 5.3. Then the next CSM is 8, right, at the bus A. So then for 8, what is the operating time? It's somewhere here. So that value is, sorry, you can take it as 0.67, right? So then you can see that the coordination between these two relays, the relay B operates at 0.26 for a fault at B, and then relay A will operate at 0.85, so that there is a good grading margin, and then the relay A will not operate unnecessarily for that fault, right? So also the advantage here is that when you are again going further towards the source, operating time starts to decrease. You can see that 0.85 to 0.67 decrease. So this is what we have drawn here in the previous figure, this one. See? The operation of the relay from C to B, it was decreasing, and then we put a grading margin, and then from B to A, again it is started to decrease. Now we reduce that impact on the relays, like let's say initially that the problem was the relays closer to the generator had longer duration time of operation. Now again we address that issue through this curve. See, again the time drops when you are coming closer to the generator. Because of this grading margin, then you definitely that will introduce some delay, right? But that's, you can't avoid it. Okay. So that is how one can work on this sort of design. You can have multiple relays, not 2, 3, 4 relays, and then you can coordinate them, right? So this is a part of your PSCAT exercise as well, where that you need to do some analysis or some calculations similar to this, right? So we have some tutorial questions based on that, and then today on Friday I will introduce a little bit on impedance relay, and then we can discuss a couple of questions on the impedance relay as well. So this is called overcurrent relay, right? Overcurrent relay, where that the working principle is basically the current measurements, right? And then the coordination of overcurrent relay is the section that we covered today, right? How do you coordinate 2 relays? And then you can coordinate multiple relays in the same way, right? So there are, I think, questions in the previous week tutorial, so we will cover those questions as well. Okay? Any questions? So if you think about the fault current calculations, those are important when you come here at this point, because you can see that maximum minimum fault currents, I have given it to you, right? So that is the point where you need to calculate those currents when you are doing real design.
Thank you.
Okay. Okay, everyone on Zoom, thanks for joining. We are going to switch off. Any questions? No. Good, all good. Thanks.
Okay. I just have one question.
Yeah.
So below 0.2 here, we're talking about
It's 0.2.
yeah, no, like the TDS.
Yes, TDS curve. If you go here, 0.
Right. So the idea is we started with this.
With the lowest, whatever the lowest.
And then after that, we see we have the M ratio for the second one. We just got intersect, like we just move up because of the
Yes,
margin.
because of the margin, not here, this one.
Yeah, so yeah, this. We move up to the margin. and
Whatever the to the next curve,
Right.
right? And then where that you touch this one, the next curve, and then see that point is above this or below this.
Right.
In this case, it was above, right? If it is below, then you need to go to the next one,
Okay.
right?
If it's below,
Below.
mean if it's
This point,
right.
let's say, was here,
Or like we went past the blue
Yes,
line.
yes.
Okay.
right? The blue line is below the required point.
Okay.
Yeah.
Okay.
Then you go to the next one, right?
Yeah. Okay.
Yeah.
Thank you.
Yeah. Nice.
How are you?
Good. Good. How are you doing?
So far good.
Did you have a lecture now?
Yeah.
You were not here last week, I think.
No. It's a 4th-year course and we share it, and my colleague did it via Zoom.
Oh yeah.
So
I think first day there was one. But
yeah,
then,
the first one it was Thierry, so
Yeah.
he's the course coordinator, and he will take over then after me.
Yeah. Yeah. This is also finally a close, but not many students are coming these days. they're on Zoom, and then
I'm curious how many will come. I've also forgotten to mention that I will come. So I sent them this morning an email
okay.
via Blackboard.
Hopefully they'll be here.
Well, let's see.
Looks like
Let's see.
that's.
Otherwise,
Like I
otherwise
can't
I will
see. The
feel
problem
fine.
with me is that when in the Zoom, I feel like I'm talking to myself.
Yeah.
I don't know. It's really hard for me. Like
It is hard.
right, and the engagement is not there, as even from my side, I think. So hey, at least a couple of kids are coming. The others are in Zoom, and then others are listening to the recorded ones, right?
It even happened to me in a meeting with industry partners not long ago that I
Yeah.
gave a little presentation.
Yeah.
And they dropped out and I didn't realize. So I continued with my presentation. They tried to call me,
Yeah.
but I didn't know the number, so I just switched it off. So I called back and continued. Once I was finished, I realized that,
Nobody
that I
was
was
there.
talking to myself. And the dog who was sleeping in the corner. Yeah, and it was right at the beginning. So I talked 20 minutes just to myself. Can you
So
imagine?
why they drop every?
Yeah, it was via Teams, and I think it was at the day when there was worldwide a problem with Teams.
Ah, okay.
Yeah, it was a couple of weeks ago.
Yeah.
And but yeah, to some degree, it's funny.
Yeah, but then-
it is somehow also kind of maybe. Yeah. But we can't turn the time back. It will stay. So we
Yeah,
need
it
to
will
think
stay.
how to
It
do
will
that
stay.
in a way that students kind of.
The thing is that the learning is not one-way thing, right? It's like teacher as well as the student should involve in that,
Yeah.
right?
And there is a Latin proverb, learning by teaching. So
Yeah.
whenever you teach and engage with students, you learn also a little bit yourself.
Oh yeah, of course,
Yeah.
always.
And
Always.
this gets lost in if
Yeah.
there's-
And then the other thing is that when you are dealing with Zoom, please carry on. Because this takes a while to log in. If you want to log in through this.
Yeah, I need to. Oh no, I think I will only switch to here.
Okay, so you don't do this recording here, or?
Yeah, I do recording, but I simply started through Blackboard.
Ah, okay.
Yeah,
Okay.
there is a Blackboard link,
Yeah.
and
So you are using your own machine for the Zoom as well, right? Yeah. Zoom.
yeah, that is a good point.
Because what I do,
I would need to log in
I
here
get,
to get. Yeah, this is a
that's
good
what-
point. Yeah.
This takes a little bit longer to log in. Because I came 10 minutes early, but the door was locked.
Ah,
Yeah. It was open 5 minutes to 8.
yeah.
And then I came 10 minutes earlier because usually this takes for me 6-7 minutes.
Oh, really? That long?
Yeah.
Yeah. To be honest, I used only Zoom for teaching from home. Never here. That's the very
okay.
first time for me that I give a lecture,
Yeah.
hopefully in front of at least one student.
Then
And,
I can
and-
help you.
So
Oh yeah, it's quite fast.
yeah,
this
it's
time.
already. There was a link to.
Yeah. You just go to that, double click the Zoom one. No. Can you close this one?
Yeah.
Yeah, this one. So then it will take you to the Click login. Yeah.
Simple.
By the way, I'm Chandiman.
Alex, nice to meet you. From Civil.
Oh yeah, from Seoul.
Yeah.
I'm from electrical.
Ah, okay. So do you work with Amin? Or?
No, I'm in the other side, the Tapans, the power engineering.
Ah, okay. I can ask you a question. For some reason, I inherited a master student
Uh-huh.
who want to do some grid simulation for renewable energy. I don't know why he ended up with us. Yeah, and I was not the first one. And I was not the first one.
So civil
who-
engineering is doing.
Yeah. renewable energy, and to some degree, I don't know,
Yeah.
he thought he needs to do some simulation. Do we have at UQ a program, a simple program for students to do these kind of grid simulations?
Yeah. Yeah.
Huh?
Yeah. We have.
Ah,
Yeah,
okay.
yeah.
What is it?
We have one called PSCAD, another one called PSSE, but then it's, you have to build the, like, I don't know whether
Everything from the scratch.
like, there's no, like, let's say some people have Queensland model,
Yeah.
right, but then they developed it,
Yeah.
right? I don't know whether they are, they will share it, but if he wants to do something, probably they can do it on a small scale system.
What is this now?
That's your that thing. No, timed out. Try again.
Try again. Of course.
Oh yeah.
Yeah. There we are.
And then do not trust the browser. Because I don't know, I never trust this machine.
Yeah, you never know. Yeah.
It's fine, but yeah. And then you said that you have that link name.
Yeah, I have the link here.
But
But
so go to the join and type that number there.
Where is it? Learning resources. Oh, that was too much. Learning resources. And Zoom link to lectures.
Yeah, that's the number. Just cancel it, otherwise that guy will. 849 66 703 19. Oh. 849
849
66
66
703
703.
193.
Okay,
Yeah.
there we are.
You are in computer edit. So just cancel this one, otherwise.
Yeah, but I need them to probably.
Yeah, you
Go
can
in
run this
there.
one here, the presentation, and then you go to the share screen, advance, here, and then you need to, yeah, it's okay. Do you have the presentation slides?
Yeah.
And then you need to connect, do you have a connector? Did you connect the...
Yeah, it's already connected. Yeah.
Yeah, just